Okay. As is traditional with me, I like to say a couple things about the homework first homework set, ostensibly do what we Friday. This is stimulated by like kind of some of our early stuff. See if you can give an example of a commutative ring, and of course it will necessarily be that identity, that does not have a maximal property. So no matter, and of course, I don't consider a maximal ideal to be the whole ring itself. Otherwise, what the heck are we talking about? So you build a ring where there's no maximal ideal. So whatever ideal you find in there is the one that's slightly bigger, but not the whole ring. Number two is kind of an important thing that maybe you've seen in 8510 or maybe not. So I'm going to highlight this. Suppose you have a commutative ring with identity that let I and R be a proper ideal. We define the radical of I to be, how many of you have seen the radical? Right? It's the set of all crap in the ring, such that a big enough power will land you down in the ideal, right? But you may not have seen this, that, how many of you are familiar with this? Radical I is the intersection of all prime ideals. And that's actually kind of that's a useful thing to know, that the radical of any idea is actually the intersection of all primes. One of the containments here is pretty easy. And the other one will require something equivalent to Zorn's lemma, or one of the things that we've shown in multiplicative sense. Numero 3, let R be a commutative ring of identity. We define the Jacobson radical. How many of you have seen Jacobson radical? Well, actually, so let me segue back into this. Here's an interesting thing. So if you hear me now and believe me later, or if you believe me now and hear me later, what would the radical of the zero like? It would be the intersection of all the prime ideals. And from the point of view of old school, what radical is, it's what is the radical of zero like this? It's a set of nilpotents. Right? Because it's everything of big enough power is zero, right? So the nilpotent elements in the ring actually form an ideal, and they are the intersection of P all primes. So that's kind of an interesting corollary problem too. The nilpotents should be the intersection of all stinking prime ideals in the ring, right? And as a corollary, the nilpotents form an ideal, right? So the nilpotents, or sometimes it's called the nil radical by some authors, are the intersection of all the prime ideals. What is the Jacobson radical? The Jacobson radical intersects all of the maximal ideals. So I would expect that, of course, all the maximal ideals are prime. So I would expect the Jacobson radical to be a little bit bigger in general than the nil radical. Of course, sometimes they can be the same. If you look at the intersection of all the prime ideals in the integers, well, you get zero because one of the primes is zero, right? In fact, in any integral domain, nil radical will be zero. But in the integers also, the Jacobson radical is also zero because the maximal ideals are the non-zero primes. And since there's no non-zero integer that's divisible by infinitely many primes, that intersection is zero. Can anybody give an example of a ring with a non-zero Jacobson radical? What's that now?
Some non-domain, not a ring that is not an integral domain. So just take the direct
Can you give an example that is an integral domain?
ZP times CP. Basically, direct sums.
What do you mean when you say CP?
Oh, finite theories. Direct sums, some finite.
Well, if you had meant p-adics, that would be okay. And yes, you're right, the finite fields was also okay, but that actually has a zero Jacob's radical, right? Because there's only one ideal at all.
Oh,
How about this?
That is equivalent to say, they are the same.
What's that?
So this ring is actually can be sort of chaotic.
The power series ring?
Yeah.
Well, I wouldn't say p-adically, I would say x-adically, but yes, that's right. Yes, the p-adics, if you're a real number theory junkie like that, doesn't matter, we might talk about that later. The p-adics, for the power series, here's why the Jacobson radical is not zero. There's only one freaking maximal ideal, right? And there you go. So the maximal ideal is just the ideal generated by x. Z localized it being. Right? For example, Z localized it to the set of all fractions that have an odd denominator, right? That has a unique maximal ideal. So there's lots of these things. But here's an interesting characterization. Show that, so you've got this Jacobson radical thing. It's an ideal because it's an intersection of ideals. In particular, it's the intersection of maximal ideals. Show that an element, show that X, an element of the ring, is in the Jacobson radical of R, if and only if 1 plus Rx is a unit for every R in R. That's kind of a neat thing. And finally, in this kind of intersection and multiplicative sets, this is actually a rather important result too. Let R be an integral domain and N the maximal ideal. Recall, we're going to talk about localizations today, so we'll get this up today. I think. Recall R sub M. This is the set of fractions R over S, where R can be anything in R, and S is something that's not in M. Right, so it's anything outside of maximal ideal. This is a ring that contains R, or can be construed that way. Show that R is the intersection of R localized N as you range over all the maximal ideals of R. So that should be a fun. Okay, any questions on that? All right. So, let me turn this. Oh, but I wouldn't refer to you. Okay, so let me draw your picture of what we were doing last time. Let's get them pictures here. We had this theorem that said, okay, suppose you have R, right, the ring of identities. You have some idea of your I, and you're also lucky enough to have this multiplicative set here such that I intersect S. Then we have this result. We can expand I to a prime ideal. The maximal with respect to property the intersection. So in other words, what I can do is I can grow this to a slightly bigger, well, maybe you can do the same ideal, but I can grow this actually to a prime ideal that is maximum with respect to the property of missing S. And what I mean by maximum with this property is if I add any other thing to this ideal, it will pick up stuff that intersects S. By the way, maximum with respect to this property. This is actually a very important theme in commutative algebra. if you've got a good property, it often determines prime ideals. Let me give you some examples. If you have an ideal that is maximal with respect to not being finitely generated, right? So you can't generate it finitely. If you've got an ideal that's maximal with respect to that property, it's prime. If you have an ideal that is maximal with respect to not being principal, it is prime. And so you often, this is often kind of a good sort of litmus test to tell whether you've got a good property. It's something that's maximal with respect to the property is prime. So last time what we did, we showed, or we used Zorn's limit to show we established via Zorn that there exists an ideal P containing I such that P is maximal with respect to and that was kind of a big fight last time. We did Zorn's limit and expanded it, and so the only bit of the theorem that we have left is the show and this is real grouping little results here. So suppose you have two elements of R, so it's the product of C P. By way of contradiction, let's suppose A is not in P. Suppose that neither of these things are in P, even though the product is, and I want to get a contradiction out of this. Okay, so let's see what happens. Well, note notice that if you assume that A and B are not in P, then the ideal generated by P and A must strictly contain P because in particular it contains A, and the same thing with PB. Right? And so what does this mean? By maximality with respect to this property, it must be the case that, let me see if I can get everything right at the start. So there exists S1, S2, and S, and R1, R2, and R, and P1, P2, and P, such that let's see, P1 plus R1A is S1, and P2 plus R2B is S2. Right, and all those equations represent is the fact that the first one represents that the ideal generated by P and A must hit something in S. Right, so there's something in P1 plus R times something in A that hits S, the same thing. B, right? Now, just go back to high school and multiply these just flat out. And so P1, P2 plus R2, P1B plus P2, R1A plus R1, R2, and B equal S1, S2. Right. Just flat out multiplying. Now, of course, this is in S because we're assuming that S is a multiplicative of a closed set. However, this is in P, and this is in P, and this is in P. And it's obvious because these are all full of P. How about AB though? Remember, our assumption is this is so S1, S2, S intercept P, which is the empty set. So we conclude that it's any questions? Yeah, I think that's really kind of pretty stuff. Okay, any questions? So there's one thing about multiplicative sets. If you can find an ideal that is disjoint from them, let me give you a corollary. I can't exist. So here's an unnamed corollary. Any you can bring with one. Let me give you a new string on through. Let I be the zero ideal. And let S be set one. Right, one is certainly multiplicative with both set. Previous theorem. I is contained in P, and P is maximal with respect to not containing one. Right. So to miss that set, it just has to not contain one. Hence it is maximal. Right, because an ideal that is maximal with respect to the property of not containing one means it's maximal property. So there's kind of nice, and that really, that's another kind of hint. I think that you've got kind of some good properties going on when you can kind of pound out something that was a little bit more, something more elegantly like that. Okay, here's another important property. Here 143. Let S be a subset of a commutative ring with identity. Here, we'll assume 0 is not an S in this case. Then S is saturated and multiple close. Well, I'm assuming multiple close the first place. All right. It's saturated if and only if. Actually, let's say that I think I am going to say both because I want to show where kind of think both close ones. S is saturated and multiple close. if and only then. S is the complement of a set theoretic union. Of prime ideals. That is to say, as complement some of the prime ideals. Okay, so let's prove this. By the way, before we do it, I think it's kind of good to familiarize ourselves. Let's go ahead and do this. I'll look at the powers two plus or minus. This is actually multiplicative. What's it to complement? Yeah, that's right. S is the complement of everything that's not in S. Everything that's not in S has not defined class. Because basically what I've done there is I've put in powers to it. Right? So everything in the complement of S is not defined class or hence is in. So it's a complement of this collection. Right? So let's prove this. Suppose as saturated and multiplicative. Want to show that the complement of S is a union of some function of prime ideals. We need to show that complement is the union of some collection of prime ideals. So let's let X be in the complement. I proclaim that X intersect that set is in. Now, okay, I get it. X is in the complement of S, right? So it's not in S. But why is it the case that every multiple of X is not in S, right? Right, this is, so I get it. X itself is not an S, but how do I know that there isn't some RX that's an S? Yes. That's exactly the RX. Right. So the entire idea of generated by X has to miss it, right? Now we apply right there, right? So we can expand. As to the prime ideal. Yield X. Such that E of X intersect S. Throw that to a prime ideal, which the maximum is X. Notice that on outline. I claim that what we have. And so now I'm gonna have S complement is the union of these particular ideals. Let me see if I can convince you reasonably at this. Notice that each PX is the PX intersect S is empty. Therefore, PX contained S complement. So the union of all the PXs contained S complement. Right? And the other containment is easy because now if X is in S complement, then X is in PX, which is in U. And so this is like equality. So if S is saturated multiplicative flows, what do we have? We have that S complement is a union of its prime ideals. Notice that what was important for this theorem, even though it's in a very small, silly place right here, is the saturation. Of course, the theorem that we have, but the fact that it's saturated is what stands out here. Let's do the other direction. From the other direction, suppose FC is a union of prime ideals. We need to show that S is saturated multiples, right? First, let's let S be S. So S and P are not in any of primes. Right, they're not in any of the primes in complement of S. Because, for example, if S is in a prime that's contained in a complement of S, then that's a contradiction. That's a direct contradiction, right? So SP ST cannot be in any primes either. Why not? Well, because if so, because the fact it's a prime ideal, if the product has T is in there, then one of those two has to be in there, and we already said it could be in there, right? So in particular, now, so it's multiple close. Now, what about saturated? Well, now suppose X, Y is in S. But suppose that X is not an S, right? That is to say, suppose it's in constant. Well, what does that mean? So X is in some P that's contained in SC, because SC is the union of primes. Therefore, XY. And so that does the other direction. So saturated multiple close. Now, there's something interesting here, which is why I'm glad I got the whole proof. And that is, in the other direction, what was important? Well, to get the to get the multiplicative with close clause, we really needed this. It's pretty easy to see how this fails. It's not a prime ideal because the product would be in the ideal without either one being in. Prime is essential for the multiplicative close. Prime is not essential for the saturation, right? The only thing that matters is P is an ideal. It doesn't matter. So that's, I think that's what matters. Let me give you a quick definition that I've already given you, but I will put this down kind of for the record. Oh, by the way, shameless plug. I would highly encourage you to that. Right. Michael Burr's doing the first one. He's an interesting fellow, and he's doing this origami thing. And origami is like, I mean, yeah, you think of this art, it's incredibly mathematics, right? And the culmination of this is Math Club after hours, and we're gonna make a good decade. So it should be fun. So, unpickable domain, you see, now is atomic if every non-zero, non-unit R, and R is a product of atoms, which is synonymous with purity. I gave you some examples the other day of stuff that wasn't atomic or things that can't be factored in atoms. Those are actually kind of hard to come up with. How many of you, I know you are, John, anybody else working with Carrie? Well, that's right, and I knew that too. So if you work with Carrie, I'm willing to bet you're doing the theory of rings, a lot of that, right? Any theory of ring is atomic. So of all the ideals you found out in general. So about anything that you would sort of encounter on the first pass of your journey and community algebra would probably be atomic, because it's actually fairly difficult, in first principles to make something that doesn't factor into atoms with the standard ring constructions. But of course, things that aren't atomic are just like, transcendental numbers, right? They may be hard to find, most of them are, right? Definition. Definition. Is a UFD. Unique factorization. Actually, and this also illustrates kind of another important thing to be about, I think, is generalizing stuff that's cool, right? I mean, the first ring is not good, but you almost that you encounter quite the integers, and there is a whole host of reasons why the integers is a great ring, right? One of them is this property. It's a so UFDs generalize the integers in the sense that you have a fundamental theorem of arithmetic. That is, you can factor anything that's not zero and not invertible into a product of primes. But I'm willing to bet that the first definition that you saw, if you didn't see it in the number theory class, was probably something like this. R is comic. And they probably said that in your definition, although they probably didn't use that terminology. Right? They said, oh, everything factors into irreducibles. And given the irreducible factorizations, alpha 1, alpha 2, alpha n, beta 1, beta 2, beta m. And what I mean by irreducible factorizations is all these alphas and betas are assumed to be irreducible elements in the ring. We have two things. Number one, N and M are the same thing. So the lengths of factorization is. And number two, I'm going to write down a fancy way of saying basically you can pair everything off. There exists sigma in Sn such that alpha I equals ui beta sigma I. Where ui is u naught. Okay, words. What does it mean? Sigma and Sn, what that means is permutation. So each alpha I can be paired with a unique beta I over here, and alpha I and beta I are the same thing. Alpha I and beta sub sigma I are the same distinctive thing up to a unit, right? And this allows us to do things like, this allows smart aleck people from saying, oh, look, the factorizations aren't unique, right? Because you can pair these off. And for each pair, they're not the same, but they vary by a unit. In this case, going in close to right? That's essentially what it means. It means the lengths are the same, and once you got them lined up, if you rearrange what's on the right, you can pull them off in pairs. Okay. So this is the classic. How many of you, I am curious, how many of y'all saw this definition or something equivalent to it the first time you saw it, right? And they might have, if you talk about an algebra course, they might have really done it in terms of irreducibles instead of primes. The definition for UFD in terms of primes is actually much simpler. And we'll get to that. So this is, I consider this is the classic definition, right? Let me kind of expand our territory a little bit by making the following observation. Proposition. One, six. If R is a domain, and X in R can be represented as a product of non-zero primes. And, this representation is unique. And let me put a little caveat here, up to rearrange. And unit multiples. This is actually a really interesting statement. Let me throw an example at you. Y'all remember this one? This is basically polynomials that are missing the linear term. Notice that X6. So we talked about this before, but let me do this in the context of what it resolved. Now we argued before that X squared and X cubed are irreducible, right? We did this kind of degree thing. So well, you can't break it down anymore because they're only linear terms in this ring. The lengths of these factorizations are not even the same. There's 3 irreducibles here and 2 over here, right? And so what's immediate to me is this is not a prime factorization because you cannot pair these off. It's not unique up to rearrangement and unit multiples. These two, this mess up here is, right? Because I can rearrange and pair off the multiples and it's good to go. Right? So this is a powerful theorem because it says that regardless of the ring, I don't care what ring you're in, if you have some element sitting there in your ring, and that element is a product of prime factors, that's the only way to write it as a product of, in fact, irreducibles. Right? And so let's prove this, and we're going to go by induction. We will proceed by induction on number of prime factor space. One, we have X is prime itself. And because you can't break that down, and so the only way, there's no other way to factor it into irreducibles at all other than X itself. So assume that for all k between 1 and n, that if you can write X. One, two, three, PI. PI non-zero prime, and this representation is unique up to units and rearrangements. Factorization is up to even multiples and real quarter. Now assume that we have a product of impulse. PI non-zero prime, and assume that we can write X with each pi I irreducible. So actually, I'm proving something even a little bit more general than I claimed, right? But I'm assuming that you can't even redo it as irreducible. And so, so what we have P1, P2, PM plus 1. I'm sorry, that should be N plus 1 is pi 1 pi 2. Notice that as P n plus 1 prime, then P n plus 1 divided by n without extra prime. I mean, actually, P n plus 1 has to divide one of these animals, so I'll just say it by n. I lost generality. And so, pi m is equal to P n plus 1 R, but as pi m is irreducible, R is a unit of so pi m is a unit multiple of P n plus 1 and in front. Right, because any new multiple primes is prime, that's easy to verify. So if pi m is P n plus 1 u a unit, I change the R to a u just for emphasis. then cancel those out, and I get P1, P2, of Pn, pi 1, of the pi n minus 1, n. And now, why induction hypothesis? The induction hypothesis says now that in fact there now has to be m minus 1 has to be n, and these all have to pair off to units. And so that property that primes have is a little bit stronger. They have to divide one of the elements of the product. You can see it's much stronger than irreducible because, for examples, we can have very many irreducible factorizations. Prime factorizations, if they exist, unique. Okay, any questions on that? Any questions? Yes, sir.
What is it about Memphis one and that allows us to take that out? It feels like we're using factorization to that. So they're not units, so we actually can divide out by the.
But we're in an interval domain, right? And so
subtract
right
over.
here, yeah, so, right, exactly. So this is actually now, and you can cancel. And that's what allows you to do the induction. So clear it up. Other questions? All right. Well, you all have a good one, and we will catch you on